Yo, what up? Welcome to Made by Ozzy. I'm Ozzy. So if you're just turning into the channel, we are working on turning this DE0-CV development kit into a cryptocurrency miner and a graphics rendering, like a GPU. So on the last episode, we got the LEDs down here working off of a timer. In this episode, what we're going to do is we're going to get the 7-segment displays all working so that we could control an output to them. Okay, so let's go ahead and get started. Okay, so let's go ahead and get all the pins for all of our 7-segment displays added. You can see on this dev kit, we control each bit of the 7-segment displays individually with the separate output. We actually don't have access to that decimal point, but that's okay. And there's a separate output for each bit of each display. So this is a total of 42 outputs. So I'm just going to get those added. And one thing I want to point out is the naming convention of these 7-segment displays: hex 00 to hex 06, and then it jumps to hex 10 down to hex 16, and then hex 20 down to hex 26. This is a convenient way to name it. It'll come in handy later. Okay, so I got Copper opened up, the Cordis project, and let's go ahead and add those hex new outputs I just added. And I'm definitely going to need some more room. Oh, I don't want to move that. Definitely going to need some more room for this. Okay. Hold control on copying, hex 00. And then I could increment that a couple times. 2, 3. Hex 01 doesn't seem to be naming it how I wanted it. Hex 02, hex 03, hex 04, hex 05, one more. Okay, can I copy the whole thing? Probably not worth it. Hex 10. Cordis just appears to be not behaving with me, so this is going to be a pain in the butt, I think. Yep, can't double click on him anymore. Okay, save. Okay, so now that we have all the pins set up, let's figure out what we want to display on it. So what we actually need to figure out is, what character we want on here, 1, 2, whatever, and then figure out which bits we need to turn on in order to actually show those. So we have 6 7-segment displays. Let's come up with a little simple test vector of what we could show. I think we could show the numbers 4 to 0, and then a blank space, and then a number 6, 9. I think that's a good industry standard test vector. So 420, 69. Let's see what bits we need to turn on for that. So let's go over here. Bit 0 for the 4 is going to be off, so just set that to a 0. Bit 1 will be on, right? Bit 2 here is also on. And bit 3 will be off. Bit 4 will also be off. Bit 5 will be on, and bit 6 will be on. Okay, and then just go through and repeat. Let's do it for all of them. Okay, now I got all my bits mapped out. Now I'd be done except for one little caveat, and this is where it helps to actually read the manual carefully. So this sentence right here: the segment can be turned on or off by applying a low logic level or a high logic level from the FPGA, respectively. This threw me off at first. So it can be turned on or off by doing a low or a high, respectively. So that means if we want to turn it on, we actually need to send a low level signal, which is a 0. But the way we map this out The ones that are off, I put 0 instead of 1. So I actually need to go through in this whole map and just reverse it. And there we go. Now I have all the bits that I'm going to need in order to set this on our 7-segment display. Okay, so now let's actually go write some Verilog to drive this state onto the appropriate pins for all of these here. Okay, so go here to Quartus and File, New, Verilog module. Okay, so module, and let's give this one a name, and let's call it a 7-segment display, just general controller. What it's going to have as an input is, you know what, let's give this, I'll show you a couple ways to do this. Rev A. All it's going to have is just outputs, because all we're writing is constants. So let's go ahead and make an output for each one. And I'm going to call it display here, because it's a 7-segment display. Display 0 is the whole one, so this is actually going to be a bus of 7 bits, and we'll get there. So let me just define all 6 of them. Alright, and then go add the end module. Okay, so we are going to define these as 7-bit output buses. So to define 7 bits, we always messing up my keywords. Output 6 0, display 0. Okay, and one thing, notice I am neglecting the reg keyword because I do want to leave these directly as wires. We're going to see how that works right now. To keep this clean, I'm not going to put them on the same line. Actually space them out. One more. Okay, I have outputs. Now all I'm going to do is assign them. Assign display 0 equals, and now I tell it what to assign it to. And 7 bits, define it as binary, and what's it going to be? It's going to be 1001100. 1001100. Okay, this is a big line. Let's unpack it. This keyword, assign, and I'm using the equal sign now. What's going on there? No more this, and now this assign. Okay, so this is the other data type. Before, let's open up one of the other Verilog modules we wrote in the last video. For example, this here. We were using this assignment operator with the less than sign. This is actually a one specifically used with registers. It only means something if you're using it with the register, and what it basically means is it guarantees that every operation, every assignment operation that's happening here is going to use the same value for its right hand side arguments as what entered it at the beginning of the clock cycle. Whereas this one, just an assignment operator without the less than, is in constant flux. This value that's being written out to this left hand side is never going to be a guaranteed value for a certain amount of time. It could change at any point in time. The significance of that will be much more clear as modules get more complicated and timing actually becomes an issue. To our credit, timing has not been an issue because 50 megahertz is relatively slow and we are working with relatively small logic. We will have to talk about it eventually in the future. Right now we don't have to talk about timing. We just have to understand that that's the difference between these assignment operators. For wires, this is a wire. I didn't declare it as a reg. You cannot use this type of assignment. You have to use equal. And you also have to use the assign keyword. Yeah. Now, this constant. What's going on here? So here I defined a constant in the code as just a number, 0, 25 million, 0, 1. In all honesty, I cheated quite a good bit by doing this. In fair practice, you would want to define something more like count is a 25-bit number. So you would actually want to say something more like instead of 25,000, you'd want to actually define a number of bits. That's the first number, and an apostrophe. That gives you that's what tells it how many bits ends. And now you define how you want to tell it the number. You have a few options. You have D for decimal, which is what this is, the 25 million. Or it could be B for binary, all zeros and ones. or it could be H for hex, and that would be hexadecimal, so from 0 up to 9, and then A through F. So in this case, instead of just a hard 25 million like this, I really should have specified the constant like this. If neglecting this first little bit here is relying very heavily on the tool chain provided by Quartus to optimize out my negligence in the Verilog code. But in all honesty, they do a pretty good job of that, so I'm not going to change this. I'm just going to leave a note there. Go ahead and save everything. Oh, let's give this a name while we're at it. Seven segment display. Save. Okay. I only signed one of them. This won't compile, so let's go ahead and sign the rest of them. That's 6. Okay. Give myself a little comment. This is going to be 4. This is going to be 2. This is going to be 0. This is going to be blank. This is going to be 6. This is going to be 9. Perfect. A perfect test vector. Okay. What is 2? 0, 0, 1, 0, 0, 1, 0. 0, 0, 1, 0, 0, 1, 0. Nice. Okay, next one. Zeros, all the zeros but the last one. Okay, easy. 1, 2, 3, 4, 5, 6, 1. Five, 6, 7. Okay, and then we have 0, 1, and then nothing but zeros. So, okay. Oops. 0, 1, 1, 2, 3, 4, 5. Okay, last one is 0, 0, 0, 1, 1, 0, 0. 0, 0, 0, 1, 1, 0, 0. Okay, and that's it. That's it. That's our code. This is us hardwiring a constant output to display 0 all over. I guess I should change those. Okay, and there's one more. 1, 2, 3, 4, 5, 6. Oh, I just shouldn't have added that. Okay, that shouldn't exist there. Okay, perfect. Let's go ahead and save that, and let's try and create a symbol. That'll tell us if it sure, save that as well. Made that change to it, but now it's going to try and compile 7-segment display. It's going to try and synthesize 7-segment display, and if it's successful, then I know at least my logic makes sense, and I could try and use it in my top level. Okay, successful. So let's go over here to copper.bdf, zoom out a little bit and place it right here. So let's go look for it. Well, first things first, let me actually move it to where I want it. So there it is. Let's move it into library. Okay. Let's come over here and add it with this little symbol wizard. Okay, search here. Okay, and you see all it has is outputs. Each output is a bus. And earlier I mentioned that the naming convention used for the outputs, this hex 0 through hex 6, hex 1 through hex 16, is going to come in handy. And this is where it's going to come in handy. So now what we get to do is just draw the bus line here. And we get to just type hex 0 and then define the whole bus. 6 down to 0. Perfect. Alright. And for the next one, we're going to do something similar, but of course it's going to be hex 1. But again, we define the bus. So note that when you're drawing the line or the wire or the bus line in the schematic diagram, that the notation for vectors is different. Use this dot dot instead of the colon. I mean, it is what it is, right? So just note it. Hex 3, 6 dot dot 0. All right. Hex 4, 6 dot dot 0. And hex 5, 6 dot dot 0. Okay, save. Okay, now let's see if this compiles. Okay, awesome. It's finished. And let's take a second to talk about this. I haven't talked about this compilation report that gets generated when we compile a new project. A couple of key things to look at here are the total number of registers and total number of logic utilization and ALMs that you have here, and total number of pins, although that's mostly dictated by the hardware you have connected to it, so it's not a huge deal. Um, we haven't really gotten into using any of the other stuff yet, such as even PLLs or block memory or anything. In fact, this is really the only thing we've been using, the number of logic circuits we have available to us and the number of registers we have available to use. This is going to be our main limitation when we start pushing our FPGA in more demanding applications like the crypto miner or like the 3D rendering. This number, it's 33. We're at less than 1% utilization. 33 out of 18K. We got lots of room to grow, but you'll find we'll end up using stuff pretty quickly. So let's open up the programmer, go to Tools, Programmer. Okay. Oh, no hardware. I guess it would help if I turned my FPGA on, right? Okay. Now go ahead and write it out. Let's see if it worked. Okay, well, we have an output on the 7 segment displays, but that is not exactly the test vector we were anticipating. So what went wrong? What's going on here? One giveaway actually. Well, we got two giveaways actually. That's going to tell us how to get closer to what we want. Um, the first being the third from the right uh, decimal display or 7 segment display here. Um, it may be hard to see in the video here. I'm seeing the light is sort of drowning it out. But this one should be a 0. So all of the outermost pins should be lit up. But instead what's happening is all but one of the outermost pins are lit up, and then the middle one is lit up. So that's a clue that's going to help us, because otherwise the rest just sort of looks like gibberish. So let's try and use that clue and see if we can figure out what we did wrong. So if we come take a look at the manual here, um, what we noticed on that pin where the 0, it should be a 0, so all the outermost ones should be lit up, which means bits 0 through 5 should be lit up and 6 should be off. Instead, what we had was 6 was definitely on because that's in the middle, but either 3 or 0 was off. And I'm pretty sure it was 0. Yeah, it's definitely 0 that was off. So that's interesting. Where we should have set 0 through 5, we ended up setting 1 through 6. So that's a pretty big clue there. And the main giveaway is that when you are declaring a binary constant number, you're always declaring from the most significant bit to the lowest significant bit. So this should be in the order from bit 6 to bit 0. But me in my haste, I actually put them in order from bit 0 to bit 6. So that means the order of all my constants needs to be reversed. So I'm going to go ahead and do that now. Looks good. So in this situation, I actually do have to. Well, let's see if I can create. Will that update it in place? Let's see. I'll run through this whole process and check it. Update. So because I changed the logic in the Verilog file, I need to actually come update the schematic file, this BSF that we created, to use it in the schematic diagram file. And this is asking how would I like to update it. If I have multiple instances of this logic, then do I want all of them? I only have the one, so there really is no difference between all these options. So okay, and that should do it. Save and compile. Okay, all done compiling. Let's open up our programmer. The SOF should be updated, and it. Okay. Okay, well that's a lot better. So at least it's actually putting out the right characters, just not in the order we would want it. 96 blank 024. That's clearly gibberish, and we need to reverse it to read the proper test vector of 42069. So all that means is we need to go, instead of from hex 0 to hex 5, we just sort of need to reverse the order of our outputs. So let's go do that. Okay, so in order to swap the order of the characters being displayed on there, I just need to switch this here. So let's change this to the last one. That'll be 5. This will be 4. 3, 2, 1, 0. Okay. Save and compile. Copper.cdf. Okay, so what is that CDF real quick? That is this here. So all the settings used when you write an SOF out to a chip are comprise this file, the copper.cdf. And it updates every time we compile because this file itself is physically changing, copper.sof. There are other parameters that could change, such as this the device, but mostly it's like the checksum that's changing because this file is now physically different. So yeah, we want to save it because yes. File save. Okay, now let's compile. All right, successful compilation. Let's open up our programmer and go ahead and write it out. All right, woohoo, there we go. There's our first successful test vector on our 7-segment display, 420 blank 69. We know we got everything mapped right. We know we got our bits operating, our test is working, so that's great. Okay, great. So now we got our project Copper all updated with all the outputs that we need to control these 7-segment displays. We have everything proved out. We know it's working, it's mapped right, and we can control it. And Copper went ahead and reviewed and approved all the work, so we know it's good to go. All right. So in the next episode, what we're going to do is we're going to build a hex decoder. So we're going to turn the characters 0 through 9 and A through F. We're going to develop a mapping for the 7-segment displays for those characters and build a Verilog module so that we can actually take a 4-bit input for a hex number and spit out the 7-bit vector that we need to control this 7-segment display. Okay, hey, and if you like this content, go ahead and hit that like button. That help out the channel and everything, and subscribe so you could see when the videos are coming out. I'm trying to put these out pretty quickly because we got a lot of work to do until we could get to the point where we could actually turn this into a useful crypto miner and GPU, and I'm really eager. I want to get there. I want us all to get there. If you are just catching up, you could always just go sync up with the GitHub and you got everything available at your fingertips right there. Okay, this has been great. I hope I could see you guys next week. So just a friendly reminder that I did make madebyozzy.com for a quick reference for things, the GitHub, the user manual, if you want to contact me. And then, of course, if you like the content and you feel like helping me out and contributing, you could find all of my crypto receive addresses on right here.